Welcome to the deep dive. Today we're embarking on a truly incredible journey, one that might actually surprise you.
Oh, how so?
Because the concept of artificial intelligence, it isn't some recent invention, something that just popped up with the internet.
Right.
Its roots stretch back thousands of years,
Mm.
long before computers were even a glimmer in anyone's eye.
Mm-hmm.
Imagine ancient bronze guardians, maybe animated clay figures. That's where our story actually begins.
Yeah, that's right. The idea artificial life, artificial intelligence, it's incredibly deep in the human imagination.
So like mythology.
Exactly. Take Greek mythology, you've got tales like Talos.
Talos, the bronze guardian of Crete.
That's the one. Forged by Hephaestus, the god of blacksmiths. Protector, right?
Yeah.
Circled the island 3 times a day.
Wow. And how did they stop him?
Well, the story goes, they removed a plug near his foot. His life force, this ichor, just flowed out.
Huh. And it wasn't just Talos, was it?
Not all. Think of Pygmalion.
The sculptor whose statue came alive.
Mm-hmm. Or, fast forward a bit, medieval legends. The golem.
Right, the clay figure, animated by, what was it, a piece of paper.
With God's name put in its mouth, but it couldn't speak.
Interesting limitations, even.
Definitely. And the alchemist Paracelsus, he described a procedure for an artificial man. Goethe gave us the homunculus later on.
So these weren't just, like, simple fairy tales.
I don't think so. They really show this profound human curiosity, maybe even a desire to create intelligence, even in myth.
Which carries into fiction, obviously.
Oh, absolutely.
Yeah.
Mary Shelley's Frankenstein is maybe the most powerful early example.
A classic.
And then later, 1920, you get Carol Apex play, R.U.R.
Rossum's Universal Robots. That's where the word robot comes from, isn't it?
That's the one. It literally introduced the term to the world. And you even had speculative essays like Samuel Butler's Darwin Among the Machines, really pushing the boundaries.
Okay, so myths, fiction,
Yeah.
but people actually built things too, right? Automatons?
Oh, yeah. Master craftsman, you had Yan Shi in ancient China, hero of Alexandria.
Hero, right? Known for steam engines and stuff.
Mm-hmm. And the really remarkable Al-Jazari, way back in 1206 CE.
1206, what did he build?
Programmable automata. Think about that. Programmable machines almost 800 years before modern computers.
That's incredible.
And later, Jacques de Vaucanson, Leonardo Torres y Quevedo, creating these amazingly realistic humanoid automatons.
But was it just seen as clever clockwork? Or something more?
That's the interesting part. For many, especially with ancient sacred statues, there was this widespread belief that they were genuinely imbued with real minds.
Really? Like actually alive?
Or possessed, maybe.
Yeah.
Legends persisted. Virgil's palace with automaton statues, magical brazen heads that could speak.
Brazen heads, right.
Even the Norse myth of Mimir's speaking head, which Odin consulted, it shows this ancient fascination with inanimate objects having intelligence.
Okay, so we've got imagining, building, but then there's this other thread, the idea that thinking itself is mechanical.
Exactly. That's the huge conceptual leap, the core assumption. Human thought can be mechanized.
And that goes back to?
Way back. The study of formal reasoning, thinking as a structured process. You see methods of formal deduction in Chinese, Indian, Greek philosophy.
Aristotle.
Aristotle and his syllogisms, definitely. Euclid's Elements, a model of rigorous step-by-step reasoning.
And didn't you mention Al-Khwarizmi?
Yes, he gave us the word algorithm, foundational groundwork for systematic calculation.
So people were trying to formalize thought for ages.
They were. And then in the 13th century, Ramon Lull developed these conceptual logical machines.
Logical machines,
Ugh.
like actual machines.
More like conceptual devices on paper, ways to produce knowledge through logical combinations, combining basic truths to generate all possible knowledge.
Ambitious.
Very. And it influenced later thinkers, like in the 17th century. Gottfried Leibniz, Thomas Hobbes.
Hobbes said reason is nothing but reckoning, calculation.
Precisely. Even Descartes explored systematic thought. But Leibniz, he had this grand vision, a universal language.
Characteristica universalis.
Right. He thought you could reduce all arguments to calculations. Just say, let us calculate and resolve any dispute logically.
That's a powerful idea.
Yeah.
And it kind of lays the groundwork for computers, doesn't it?
It absolutely does. It articulated what later got called the physical symbol system hypothesis.
Meaning?
Essentially, the idea that intelligence, human or artificial, works by manipulating symbols according to rules, just like a computer shuffling bits.
Okay, but the really big breakthrough was mathematical logic, right?
Huge breakthrough, building on Boole, Frege. then Russell and Whitehead's Principia Mathematica.
What did that do?
It provided this massive formal treatment of mathematical foundations, showed how logic itself could be formalized.
Setting the stage for.
Well, for David Hilbert's challenge in the 1920s, could all mathematical reasoning be formalized?
And the answer was?
Surprisingly, no, not entirely. Gödel's incompleteness proof showed limits, but then you had Alan Turing's work on his theoretical machine.
The Turing machine.
Yep, and Alonzo Church's lambda calculus.
Lambda calculus. And that inspired Lisp later, right?
It did. And the really crucial insight was the Church-Turing thesis.
Which basically said?
It implied that any form of mathematical reasoning that could be precisely defined, any algorithm, could theoretically be mechanized.
By shuffling zeros and ones.
Essentially, yes. That provided the ultimate conceptual blueprint for thinking machines.
Which brings us finally to actual computers.
Right. Early computer science. People had designed calculating machines before Leibniz, Jacquard with his looms, Charles Babbage.
And Ada Lovelace. She worked with Babbage.
She did, and she famously cautioned against getting too carried away, saying the machine could only do what we ordered it to perform. Insightful.
But then World War II changed things.
Dramatically, the first modern computers emerged. Konrad Zeuss's Z3 in Germany.
Alan Turing's Colossus for code breaking.
And ENIS over at the University of Pennsylvania.
Based on Turing's ideas and John von Neumann's.
Exactly. These machines were the physical embodiment of those theories. They set the stage for something completely new.
Okay, so connecting all these threads, ancient myths, logic, automata, early computers, we finally get to the birth of AI as its own field.
Right. Roughly 1941 to 1956, a period where all these different ideas started coming together. A confluence.
What kinds of ideas?
Well, you had insights from neurology, seeing the brain as an electrical network.
Okay.
Norbert Wiener's cybernetics, focusing on control and communication in networks, machines, animals.
Cybernetics? Right.
Claude Shannon's information theory, dealing with digital signals, quantifying information.
And Turing again.
And Turing's theory of computation, formalizing what computation actually is. You put all that together.
And the idea of an electronic brain doesn't seem so crazy anymore.
Exactly. It shifted from science fiction towards scientific possibility.
And Turing himself pushed this with his 1950 paper.
He did. Computing Machinery and Intelligence, a landmark. He knew defining thinking was tricky.
So he proposed the test.
The Turing test. If a machine could chat via text, teleprinter back then, and you couldn't tell if it was human or machine.
Then you might as well say it's thinking.
That was the proposal. The first really serious philosophical benchmark for AI gave people something concrete to aim for.
And meanwhile, people were thinking about brain-like structures, too. Neural inspiration.
Oh, yeah. Donald Hebb, 1949, his idea often gets boiled down to cells that fire together, wire together.
Learning in the brain.
Basically, yeah, foundational for neuroscience. But even earlier, 1943, Walter Pitts and Warren McCulloch.
What do they do?
They analyzed these idealized artificial neurons, showed how they could perform logical functions, essentially described what we'd now call a neural network.
Wow, 1943.
And building on that, Marvin Minsky and Dean Edmonds actually built the first neural net machine in 1951, SNARK.
SNARK. So it wasn't just theory, they were building hardware.
Rudimentary, sure, but yes. They were starting to physically build these concepts piece by piece.
And not just theoretical machines or neural nets, they were building other things too, early applications.
Definitely. Things like cybernetic robots, W. Gray Walter's turtles. Yeah, little wheeled robots that explored, responded to light. And the Johns Hopkins beast. These were early analog-controlled robots demonstrating basic autonomy.
Okay. And game AI. You mentioned that.
Right. That became a tangible way to measure progress. Christopher Strachey wrote a checkers program in 51.
On the Ferranti Mark I computer.
Yep. And Diedrich Prince did a chess program the same year. Later, Arthur Samuel's checkers program in 59 was really important.
Why was Samuel special?
Because it learned. It was an early example of machine learning. It played against itself, got better, and eventually could challenge respectable amateur players. Learning was huge.
Incredible for the time. And then there was the other big approach, symbolic reasoning.
Ah, yes. The dominant paradigm for a long while. Alan Newell and Herbert A. Simon, 1955. The logic theorist.
What did logic theorists do?
It proved theorems, specifically 38 out of 52 theorems from Russell and Whitehead's Principia Mathematica.
It proved mathematical theorems.
Yeah, and sometimes found new, more elegant proofs. Simon was so impressed he claimed they'd solved the venerable mind-body problem.
But ambitious, maybe.
Huh. Maybe a little. But this symbolic approach intelligence as symbol manipulation really took hold.
And all this ferment leads to Dartmouth.
The Dartmouth Workshop, summer of 1956, absolutely pivotal, organized by Marvin Minsky and John McCarthy.
And McCarthy coined the term there.
He did. Artificial intelligence, gave the field its name, its identity.
What was their goal for the workshop?
Their proposal was incredibly bold. They asserted that, quote, every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it.
Simulate every aspect of intelligence. Wow.
Yeah. The attendees, Newell, Simon, they debuted logic theorists there. They became the leaders of AI for decades. It's widely seen as the official birth of AI as a discipline.
And it wasn't just AI folks there, right? It tied into broader changes.
Right. That same autumn, 1956, at MIT, you had Newell and Simon presenting logic theorist Noam Chomsky talking generative grammar.
Chomsky's linguistics.
And George Miller presenting his famous magical number 7 ± 2 paper on memory limits.
So, a convergence?
Exactly. It sparked this interdisciplinary shift, the cognitive revolution.
How did that change things?
It influenced psychology, philosophy, computer science, neuroscience. It basically gave researchers permission to talk about mental objects, thoughts, plans, symbols, things that earlier behaviorism had dismissed as unobservable. A new way to study the mind.
Okay, so AI is born. Then comes the first wave, right? 1956 to 74. Lots of excitement.
Intense excitement, astonishing early results, and some very big promises. Maybe too big.
What kind of result looked astonishing then?
Well, programs that could solve algebra word problems, prove geometry theorems, learn English in limited ways. John McCarthy called it the look-ma, no-hands era.
People must have thought general AI was just around the corner.
They did. Researchers like Herbert Simon, Marvin Minsky, they made bold predictions. A computer chess champion soon, general human intelligence within maybe 10, 20 years. The optimism was sky high.
And that attracted funding.
Big time. DARPA, the U.S. Defense Research Agency, started pouring millions into AI labs. MIT, Carnegie Mellon, Stanford.
With a specific goal, or?
Often, not really. Their philosophy was often fund people, not projects. Just give smart people money and see what happens. It fostered this early hacker culture, very exploratory.
So what were the main approaches they were exploring in this look-ma, no-hands era?
A big one was seeing reasoning and problem solving as search.
It's like finding your way through a maze.
Pretty much. You search step by step through possibilities to reach a goal. The problem was the number of possibilities could explode.
Combinatorial explosion.
Exactly. So they developed heuristics, clever rules of thumb to prune the search, ignore unlikely paths.
Examples?
Newell and Simon's general problem solver, or GPS, Herbert Gellinter's geometry theorem prover, and the strip system at Stanford, which planned actions for the robot, Shaky.
Shaky the robot.
Well,
what else?
Natural language processing, NLP, huge goal. Get computers to understand and use human language.
Like talking to them.
Ideally, yeah. Daniel Bobrow's student program could solve high school algebra word problems stated in English.
Wow.
People used semantic nets to represent concepts and relationships. Ross Quillian, Roger Schenck, and then there was Eliza.
Eliza the chatbot, the therapist program.
Right. Created by Joseph Weizenbaum, it could carry on surprisingly realistic conversations, fooled some people into thinking it actually understood them.
But it didn't. It was just pattern matching.
Exactly. Canned responses, clever tricks, but it was the first real chatbot, and it showed how easily humans project understanding onto machines.
Fascinating.
Yeah.
What about those micro worlds?
Ah, yes. Minsky and Seymour Papert's idea, focus on simplified situations, like the blocks world.
Just colored blocks on a table?
Pretty much. It allowed them to make progress on really hard problems, like machine vision, robotics. A robot arm could stack the blocks. Terry Winograd's SHRDLU system was famous.
What did SHRDLU do?
It lived in this blocks world. You could talk to it in English about the blocks, ask it to move them, ask why it did things. It could understand and plan actions within that limited world. Very impressive for the time.
So symbolic AI was king, but what about those neural networks, the perceptrons?
Right. They were still around, but kind of in the background. Frank Rosenblatt introduced the perceptron in '58. Single-layer neural network. He was very optimistic.
And others built them too.
Bernard Widrow and Ted Hoff built Adeline and Madeline, early neural nets. Mostly bespoke hardware back then.
But they hit a wall.
A big one. Minsky and Papert's 1969 book, perceptrons. It mathematically showed the severe limitations of those single-layer networks. They couldn't solve certain fundamental problems.
Like the XOR problem.
Exactly. And because the method for training multi-layer networks backpropagation wasn't really known or appreciated by that community then, the book basically killed funding for connectionist research for nearly a decade.
Ouch. So that optimism started to fade.
It did. The promises weren't being met, especially the big ones about general intelligence, which leads us into the first AI winter, roughly 1974 to 1980.
Winter. Sounds bad. Funding dried up.
Significantly. The earlier hype created impossibly high expectations. When breakthroughs didn't keep coming at that pace, governments, especially in the US and UK, got skeptical and cut funding for undirected blue-sky AI research.
Any specific triggers?
Well, the AIL-PAC report back in '66 had already hit machine translation funding hard. Then the Lighthill report in '73 was very critical of UK AI research, leading to major cuts there.
So labs lost money. Was it a total freeze everywhere?
Well, that's debated. Some historians argue it wasn't a universal winter. Major labs definitely felt the pinch. But public interest kept growing. The number of researchers actually increased. AI researcher Nils Nilsson even called it the most exciting time to work in AI.
So maybe less funding for grand goals, but still work happening.
Yeah, perhaps more focused work, but the fundamental problems that caused the disillusionment were very real.
Like what? What were the big hurdles?
First, just raw computer power. Or lack thereof. Machines were still incredibly slow and had tiny amounts of memory by today's standards.
You mentioned Ross Quillian's NLP work only had 20 words.
Right, because that's all the memory could handle. Hans Moravec in '76 estimated computers were millions of times too weak for human-level intelligence, like trying to fly with a lawnmower engine.
Okay, lack of power. What else?
Intractability. That combinatorial explosion problem wasn't just theory. Richard Karp showed in '72 that many core AI problems were computationally hard, exponentially hard.
Meaning solutions that worked on small toy problems wouldn't scale up.
Exactly. They'd take literally astronomical amounts of time on real-world complexities, a dead end for many early approaches.
And then there was that paradox. Moravec's paradox.
Yeah, really perplexing. AI was getting good at stuff humans find hard theorem-proving, chess. But it was terrible at stuff humans find easy, recognizing a face, walking across a room without tripping.
Why was that?
It seemed symbolic reasoning, manipulating abstract symbols, just wasn't the right tool for perception and motor skills. Those seemed to need something different.
Another huge problem. Common sense knowledge.
Massive hurdle. How do you give a machine all the basic background knowledge about the world that a child picks up effortlessly? Billions of facts. How does it learn it? Nobody knew.
And just trying to write down rules for common sense.
It became incredibly complex, endless exceptions, nuances. Logic struggled with the fuzziness of common sense.
Did anyone try alternatives to pure logic for common sense?
Yes. Marvin Minsky proposed frames in '75.
Frames.
Like templates for concepts. A bird frame might have slots for color, size, and a default value for flies, capturing typical assumptions. Roger Schenck used a similar idea called scripts for understanding stories, typical sequences of events, like in a restaurant.
Did those ideas catch on?
They were influential. They moved away from pure logic and actually influenced later things like object-oriented programming.
This period also saw philosophical attacks.
Oh, yes. Philosophers started pushing back hard. John Lucas used Gödel's incompleteness theorem to argue machines could never replicate the human mind. Hubert Dreyfus emphasized human intuition, know-how things hard to formalize.
And John Searle.
Searle's Chinese room argument, famous thought experiment, argued that even if a machine passed the Turing test perfectly, manipulating symbols according to rules, it wouldn't understand the meaning. No real intentionality.
How did AI researchers react?
Mostly, they dismissed these critiques. They were focused on engineering, building things, but not everyone. Joseph Weissenbaum, Eliza's creator,
He got worried.
he developed serious ethical doubts, especially when people started treating Eliza like a real therapist. His 1976 book, Computer Power and Human Reason, warned about misusing AI, devaluing human connection, a very early, important warning.
And within AI itself, there was a split. Neats versus Scruffies.
Ah, yeah. A fun way to put it. The NEETs, like John McCarthy, focused on formal logic, elegant theories, mathematical rigor, provable correctness.
And the Scruffies.
More like Minsky, Papert, Schenck at MIT. They were more empirical, maybe anti-logic. Build stuff, test it, see what works for specific tasks. Don't worry so much about grand unified theories. Iterate, patch it till it works. A real clash of cultures.
So, a tough period, but things started changing in the 80s. The AI boom.
Yes, the 1980s saw a major resurgence, driven by new directions and, crucially, practical applications that made money.
And the big one was expert systems.
Absolutely. These programs captured the knowledge of human experts in a specific domain, like medicine or geology, and used it to answer questions or solve problems.
Weren't Dendril and MYCIN early examples?
They showed feasibility. But the breakout hit was R1, developed for Digital Equipment Corporation, DEC, in 1980.
What did R1 do?
It configured VX computer systems.
Yeah.
Complex task. And it worked. By 1986, it was reportedly saving DEC $40 million a year.
40 million. Okay, that gets attention.
You bet it did. Suddenly, AI wasn't just academic. It was useful, profitable. A billion-dollar AI industry sprang up around expert systems. The key insight wasn't just processing power, it was knowledge.
The right information.
Exactly. Practical intelligence depends heavily on having the right knowledge.
And this success brought back government funding.
It did. Governments saw the economic and strategic potential. Japan launched its massive fifth-generation computer project in '81. $850 million aimed at machines that could converse, translate, see, reason. Very ambitious.
And others followed.
The UK had the ALVI project. The US had the Microelectronics and Computer Technology Corporation. And DARPA ramped up again with its Strategic Computing Initiative. AI was back in a big way.
This focus on knowledge, did it have a name?
It became known as the Knowledge Revolution. Building knowledge-based systems and the practice of knowledge engineering, extracting expertise from humans and encoding it became central.
Is that when Douglas Lenat started the Psych project?
Yes. Psych was this incredibly ambitious attempt to solve the common-sense knowledge problem head-on by manually building a massive database of mundane facts, millions of them, trying to give the machine basic world knowledge.
Wow. Still going today, isn't it?
It is a testament to how hard that problem is.
So symbolic AI, knowledge-based systems were booming. But the old problems didn't completely vanish.
No. Perception, robotics, learning, common sense, symbolic AI still struggled there, which opened the door for other sub-symbolic approaches to gain ground.
Like neural networks making a comeback.
Exactly. The revival of neural networks, often called connectionism, a key moment was 1982, physicist John Hopfield.
What did Hopfield do?
He showed mathematically how a certain type of neural network, now called a Hopfield net, could learn and process information, like memory. It gave neural nets new theoretical respectability.
And around the same time, backpropagation.
Yes. Geoffrey Hinton, David Rumelhart, and others rediscovered and popularized backpropagation.
The algorithm for training multi-layer networks, the thing missing in the 70s.
That's the one. Suddenly, you could train deeper, more powerful networks. This really kicked off the connectionism movement and led to intense debates with the symbolic AI folks.
Did it lead to useful stuff back then?
It started to. Jan LeCun, in 1990, used convolutional neural networks, a specific type, to recognize handwritten digits. Reading zip codes on mail, checks. A real-world application.
Okay, so neural nets revived. What else was happening outside symbolic AI?
Robotics took a different turn.
Yeah.
Researchers like Rodney Brooks and Hans Moravec.
Moravec again.
Yeah. They argued for embodied reason, that real intelligence needs a body. It has to perceive, move, interact directly with the messy real world.
Not just reason in the abstract.
Right. Build intelligence from the bottom up, they said. Less focus on internal symbolic models. Brooks famously wrote a paper called Elephants Don't Play Chess.
Meaning?
Meaning maybe complex abstract thought isn't the core of intelligence, maybe coping with the real world is. He argued, the world is its own best model. Just react to it.
Interesting perspective. What about dealing with uncertainty? Symbolic logic is pretty black and white.
Good point. That led to soft computing and probabilistic reasoning, using methods that could handle incomplete, fuzzy, uncertain information, give probably correct answers.
Like statistics entering AI.
Very much so. Judea Pearl's 1988 book, Probabilistic Reasoning in Intelligent Systems, was hugely influential. Brought probability, Bayesian networks, decision theory into the mainstream of AI. Also, fuzzy logic, developed by Lotfi Zadeh back in the 60s, gained traction for control systems.
And learning from rewards.
Reinforcement learning. Based on psychological ideas, Thorndike's law of effect, Pavlov, Skinner, trial and error learning.
Turing and Samuel thought about it for AI.
They had. But Richard Sutton and Andrew Bardo really revolutionized the field mathematically. Their work led to the temporal difference TD learning algorithm in 1988.
TD learning, what did that enable?
Famously, Gerald Tesoro's TD Gammon program in 1992. It learned to play backgammon at a world-class level just by playing millions of games against itself. No human expertise programmed in, just learning from wins and losses.
That's amazing, starting from scratch.
Yeah, and interestingly, neurologists later found evidence that the brain's dopamine reward system seems to implement a form of TD learning, biology and AI converging again.
Okay, so the 80s boom, new approaches emerging, but then things cooled off again. Another winter.
Sort of. The late 80s, early 90s saw the second AI winter, or at least a significant chill.
What happened this time? The expert systems.
The hype around expert systems faded. Turns out they were often expensive to build and, crucially, very expensive and difficult to maintain and update. They were brittle.
Brittle, meaning they broke easily.
Yeah, if they encountered a situation slightly outside their program knowledge, they could fail spectacularly, give nonsensical answers, not robust. Plus, the specialized hardware market collapsed.
Those Lisp machines.
Yep. Cheaper, faster standard workstations basically killed them off overnight in 1987. And Japan's big fifth-generation project didn't deliver on many of its grandest promises, like easy natural conversation. Lots of AI companies went bust.
So AI vanished again.
Not really. It was more like AI went behind the scenes. The term AI might have been tarnished, but the algorithms and techniques developed by AI researchers started getting quietly embedded into larger software systems all over. Data mining, industrial robotics, logistics planning, speech recognition in phone systems, fraud detection in banking, medical diagnosis tools, even early Google search relied on AI ideas.
So it became part of regular software engineering.
In many ways, yes. This led to the AI effect.
Which is?
The phenomenon where as soon as an AI technique becomes successful and commonplace, people stop calling it AI.
Huh. Like optical character recognition or something.
Exactly. As Nick Bostrom said, once something becomes useful enough and common enough, it's not labeled AI anymore. Researchers sometimes even avoided the term AI to get funding, using labels like informatics or knowledge-based systems, hiding in plain sight.
So while the public perception was winter, the field itself was evolving.
Definitely. AI research became much more mathematically rigorous. More collaboration with fields like statistics, electrical engineering, operations research led to more measurable, provable results, more scientific, less speculative.
And they focused on narrower problems.
Yes, a big shift towards narrow AI, solving specific, well-defined problems with verifiable solutions rather than chasing the grand goal of general human-like intelligence. That made progress more tractable.
Was there a unifying idea during this time?
The intelligent agents paradigm gained wide acceptance in the 90s.
An agent being?
A system that perceives its environment and takes actions to maximize its chance of success. It's a very broad definition. It allowed researchers to study specific problems, vision as perception, planning as action selection within a larger framework that still aspired towards general intelligence eventually.
And computers kept getting faster. Moore's Law.
Relentlessly. And that was maybe the biggest factor. Major milestones weren't always due to brand new theories, but steady engineering improvements plus massively increased computing power.
Like Deep Blue.
Exactly. May 11, 1997. Deep Blue beats Garry Kasparov, the world chess champion. It wasn't necessarily smarter in a human sense, but it could calculate billions of positions per second. It was 10 million times faster than that 1951 chess program.
Wow. And the DARPA challenges for self-driving cars.
Right. Stanford winning the Grand Challenge in 2005, CMU winning the Urban Challenge in 2007, autonomous vehicles navigating complex environments. Again, huge computational power was key. The raw power problem was finally being overcome.
Which brings us to, well, pretty much the modern era, the current AI boom, starting around 2005, driven by...
two huge things, big data and deep learning. And they fed each other.
How so?
Machine learning, especially deep learning, needs enormous amounts of data to train effectively. And suddenly, thanks to the internet, we had it.
Jeffrey Hinton said data sets were too small and computers too slow before.
Exactly. He recalled that in the 90s, labeled data sets were thousands of times too small, computers millions of times too slow. That flipped. You got massive data sets like labeled faces in the wild, ImageNet.
ImageNet was Fei-Fei Li's project, right?
Yeah.
Millions of labeled images.
Yep. Hugely influential. Google released Word2Vec in 2013, algorithms that learned word meanings from text surprisingly well. And just the sheer volume of text and images online. Billions of web pages.
fuel for the algorithms.
Precisely. This big data allowed systems like IBM's Watson to crunch through vast amounts of information and win Jeopardy!
Yay.
In 2011, demonstrated the power of internet-scale knowledge combined with clever AI.
And then the deep learning breakthrough.
The pivotal moment was 2012, the ImageNet competition. A deep learning model called AlexNet, developed by Alex Krzyzewski and Jeffrey Hinton's team.
What did it do?
It crushed the competition. Its error rate for identifying objects and images was significantly lower than any previous approach. It was a watershed moment because deep learning, using these multi-layer neural networks, proved much more effective, simpler, and more general than the older methods that required engineers to painstakingly handcraft features for the system to look for. Deep learning learned the important features itself from the data.
And it worked for other things, too.
Dramatically well. Speech recognition, machine translation, medical diagnosis, playing complex games like Go. Deep learning led to huge performance gains across the board. This really fueled the current boom in AI investment and public interest.
But as AI got more powerful, the worries grew, too. The alignment problem.
Yes. The prospect of superintelligent machines, smarter than humans, moved from sci-fi to serious academic discussion. Ray Kurzweil was optimistic about a coming singularity. But others, like philosopher Nick Bostrom, Eliezer Yudkowsky, they raised serious warnings about existential risks.
Bostrom's book, Superintelligence, laid out the alignment problem.
Right. The core idea. If you build an AI much smarter than you, how do you ensure its goals are perfectly aligned with human values? If they're slightly off, even a seemingly benign goal, like make paperclips, could lead to disaster if the AI converted the whole planet into paperclip.
The runaway AI scenario.
Or even just trying to achieve a goal in unexpected, harmful ways, like the robot killing its owner to fetch coffee faster, a stark illustration of the need for careful goal specification.
And these weren't just future worries, right? Real-world ethical issues started popping up.
Absolutely. Algorithmic bias became a major concern. That 2015 ProPublica report on the Compass system used in U.S. courts, showing it was biased against Black defendants in predicting recidivism, that was a wake-up call.
And misinformation. Social media algorithms.
Yes. Algorithms designed purely to maximize engagement could inadvertently amplify harmful content or create filter bubbles. These real-world harms dramatically increased research and funding into AI ethics and value alignment after about 2016. The field had to start taking responsibility.
Amidst all this, the dream of artificial general intelligence, AGI, came back.
It did. Many felt mainstream AI had become too focused on narrow AI. Pioneers like Nielsen, McCarthy, Minsky had always kept the AGI goal alive. Ben Goertzel coined the term artificial general intelligence to distinguish it from narrow AI.
And companies were founded specifically to chase AGI.
Yes, in the 2010s, DeepMind, founded 2010, acquired by Google. OpenAI, founded 2015 by folks like Elon Musk and Sam Altman.
And they were often motivated by safety concerns.
Very much so. Many founders were deeply worried about existential risk and wanted to ensure AGI was developed safely and beneficially. This actually led to intense competition and sometimes rivalries over the right way to build safe AGI. Anthropic, for instance, was formed by people who left OpenAI partly over safety disagreements.
Okay, which brings us right up to the bleeding edge. Large language models, LLMs.
The current explosion, starting seriously around 2017 with the transformer architecture.
Proposed by Google researchers, what was special about transformers?
The key was the attention mechanism. It allowed the model to weigh the importance of different words in the input text, regardless of their distance from each other. This was crucial for understanding context and long-range dependencies in language, a real game changer for NLP.
And these transformers powered the big LLMs.
They became the foundation. Companies like OpenAI with GPT-3 in 2020, DeepMind with Gato in 2022. These are foundation models, trained on absolutely massive amounts of text and code, able to adapt to many different tasks without specific retraining.
But a public explosion was ChatGPT.
November 30, 2022. Changed everything. Over 100 million users in 2 months. Fastest growing consumer app ever. Its ability to chat, write code, generate creative text, it felt qualitatively different.
And the tech giants reacted.
Instantly. Google reportedly declared a code red, accelerated their own LLM work, leading to Gemini. Microsoft integrated OpenAI's tech into Bing Search, creating Bing Chat, now Copilot. An arms race began.
Did this reignite the AGI debate around LLM specifically?
Massively. Seeing ChatGPT-4 pass complex exams like the bar exam or advanced biology tests, it convinced many skeptics, including Bill Gates, that something profound was happening. Microsoft Research even published a paper calling GPT-4 an early version of an artificial general intelligence.
And testing improved.
Benchmarks specifically for AGI, like RRC AGI, emerged. In 2024, an OpenAI model unofficially surpassed typical human scores on it. The needle was definitely moving.
Fueling an investment frenzy.
Unprecedented, especially in generative AI. Total AI investment jumped from maybe $18 billion in 2014 to nearly $120 billion in 2021 and kept climbing. The U.S. led in venture capital, startups, patents. OpenAI hit an $86 billion valuation. NVIDIA, making the essential GPUs, soared past $3 trillion market cap.
But some skepticism crept in. Bubble talk.
By mid-2024, yes, some prominent investors started questioning the valuations, the path to profitability for some AI startups, warning about a potential bubble, the classic hype cycle pattern, maybe.
And the public debate intensified. That open letter.
Right. March 2023. Over 20,000 signatories, including Musk, Wozniak, calling for a 6-month pause on training AI systems more powerful than GPT-4, citing societal risks. Huge controversy. Others pushed back, emphasizing the potential benefits.
And the technology kept marching on. New models.
Oh, yeah. Anthropic released its Claude 3 family in March 2024, with the top model, Opus, outperforming GPT-4 on many benchmarks. Then Claude 3.5 Sonnet improved further. The pace is relentless.
And finally, Nobel Prizes.
Huge recognition in 2024. John Hopfield and Geoffrey Hinton won the Physics Nobel for their foundational work on neural networks.
Physics, not computer science.
Right, underlining the fundamental nature of the work. And David Baker, Demis Hassabis, John Jumper won the Chemistry Nobel for protein structure prediction, largely thanks to DeepMind's AlphaFold AI impacting core science at the highest level.
So looking just ahead, 2025 onwards, what's the trajectory? AI meeting robotics.
That seems to be a major focus. Advanced AI, especially models that understand language and vision, are enabling much more seamless integration with robots.
Transforming industries.
Potentially. Manufacturing, logistics, household automation, healthcare. You're already seeing things like AI-powered humanoid robots helping nurses in some Chinese hospitals, also accelerating scientific discovery through robotic labs.
And governments are getting serious with strategies and money.
Big time. China, in 2025, committed around $100 billion USD towards AI and robotics, making service robots a priority in their 5-year plan. They also mandated labeling of AI-generated content from September 2025, transparency.
What about the U.S.?
January 2025 saw that huge Stargate LLC announcement. OpenAI, SoftBank, Oracle, MGX planning $500 billion in AI infrastructure by 2029, starting with $100 billion, aimed at reindustrialization, national security.
And government funding, too.
About $2 billion allocated to integrate AI and robotics in manufacturing, logistics, including defense tech. An executive order established an AI action plan. OpenAI even launched ChatGPT Gov for secure government use.
So the overall picture is
increased global investment, accelerating science, boosting productivity, transforming industries. AI seems poised to fundamentally reshape daily life.
Okay, so we've covered millennia. From myths and automatons through logic, cybernetics, the booms and winters, symbolic AI, connectionism, big data, deep learning, and now LLMs and this huge global push.
It's been quite a ride, marked by huge dreams, crushing disappointments, quiet persistence, and now this dramatic reemergence into the public spotlight.
So reflecting on all this history, what does it all mean for us, learners witnessing this crazy fast transformation right now?
Well, what's really fascinating, I think, is how consistent some of the underlying human questions have been. What is intelligence? Can we replicate it? What are the risks? Those questions echo from Talos right through to ChatGPT.
Yeah, that's true.
Which raises a big question for the future. How much of what's coming will just be a continuation of these historical patterns? The cycles of hype and disillusionment, the ethical debates, and what parts might be genuinely unprecedented this time?
That's a really interesting way to frame it. So maybe a final thought for everyone listening. How might that historical pattern, those AI winters and booms, apply to the current excitement around LLMs and AGI? Is this boom different?
And thinking about those ethical concerns raised by AI pioneers themselves, like Weizenbaum or the calls for a pause, what responsibilities do we all have, just as informed citizens, in shaping how this story unfolds from here? It's not just technology, it's about the society we build with it.